Hello everyone, I am Talha. In this project, we present ToolMind, a VLM-guided robotic pipeline for sequential tool use. Robotic tool use is a difficult task because the robot must reason about both semantics and geometry. It needs to understand which objects can be used as a tool, where to grasp it, which part should contact the targets, and which waypoints are needed to complete the task. Visual language models are useful for this because they can understand scenes, objects, and affordances from images and language. However, they are not always reliable for precise spatial grounding. In our experiments, we observed two main issues. First, even when the VLM selects the correct tool, it often predicts key points near the object center instead of the functional extremity. We call this spatial myopia. Second, without explicit cluster labels, the VLM may place points on irrelevant objects or even on background regions. To address this, we segment the RGBD scene into objects clusters using dbScan, label each candidate object as A, B, C, and provide these labeled images to the VLM. This makes the prediction problem more grounded. We also use structured chain of thought prompting where the VLM first reasons about tool geometry, grasp region, and functional contact point before outputting coordinates. Overall, ToolMind combines VLM-based reasoning with depth-based geometric refinements and comma trajectory optimization. We tested on three scenarios: wall retrieval, screwdriver insertion, and shelf retrieval.
To test our solution, ToolMind, we designed three specific constraint tabletop scenarios. We choose these environments carefully. They aren't just random laboratory tests. They are designed to expose a critical flaw in visual language models that we call spatial myopia, the model's tendency to look at the center of an object rather than the extreme edges needed to actually use a tool. Let me walk you through these scenarios, their objectives, and why they are surprisingly difficult for robots in everyday environments. Scenario 1, wall retrieval, pulling. Our first scenario is the wall retrieval task. The setup is simple. A target box sits behind a rigid wall. The robot must select a rake, grasp its handle, and drag the box into its reachable workspace. Why this is so challenging for a robot in daily life? Humans naturally understand how to extend their reach, but for a robot, it requires complex spatial planning. The robot has to figure out how to place the tool behind the box to hook it, and then calculate exactly where to stop pulling so the box is reachable. It requires reasoning about obstructed spaces and using the tool as a physical extension of its own arm. Scenario 2, screwdriver insertion. The second scenario focuses on precision, the screwdriver insertion task. Here, the robot must select a screwdriver from among unrelated, distracting objects and insert its tip into a rotating target. In daily environment like a factory, floor, or a home repair, this task is incredibly unforgiving. It requires a collision-safe 3D approach pose. The robot must hover exactly at a fixed offset above the target before descending vertically. This forces the AI to perfectly distinguish the grasping handle from functional tip. A task where standard models fail because they naturally want to grab the center of the tool instead of its geometric extremities. Scenario 3, shelf retrieval sweeping. Finally, we have the shelf retrieval task. A cup is placed under a low clearance shelf. The robot must select a sweeping tool, navigate it into a very tight gap without crashing, and sweep the cup out. This is by far the most geometrically demanding scenario. In the real world, reaching under furniture or into tight shelves means you have zero room for error. The robot must simultaneously understand the orientation of the shelf gap, the direction of the tool, and where exactly the functional contact point should be to push the cup. Our tests showed that without strict spatial reasoning, models often try to push from the wrong ends of the tool, resulting in total failure. This scenario proves that navigating tight constraints requires highly structured geometrical thinking. In short, we didn't choose these scenarios just because they look good in a simulation. We choose them because pulling an out-of-reach object, inserting a precision tool, and sweeping under a tight obstacle represents the exact everyday physical interactions where AI systems hit a wall. By solving these specific challenges, ToolMind takes a significant step toward robots that can operate not just in structured labs, but in the open, unpredictable real world.
In this part, I will explain the perception side. There are two main steps. One, obtaining 3D point cloud, and the other one DB scan segmentation. First, to get the point cloud, we capture RGBD images using our cameras. The number of cameras depends on the complexity of the scene. As you can see, we use 9 cameras for the more complex screw and shelf tasks, and 5 cameras for the wall task. These RGBD images give us both color and depth data, which we use to build our 3D point cloud. In the next step, after getting the point cloud, we move on to the segmentation. We use DB scan algorithm to group the points into distinct clusters. In the colored image, you can see that each separate object is highlighted in a different color. Finally, we turn this object knowledge into annotated images. We assign alphabetic labels like A, B, C, D to each of these valid object cluster and draw bounding boxes around them. So why are these steps so important for our project? Because we provide these annotated images and the cluster data directly to the VLM, so that VLM can decide which tool to use. We basically give these labeled objects as candidates to the VLM. If we just give the VLM a raw image without these labels, it would struggle, as the evolution study shows. Our experiments show that without labels, the VLM's predictions scatter across much larger areas, and it can frequently choose the wrong objects or just random background points.
After DB scan segmentation, each movable object in the scene is assigned a cluster label such as A, B, or C. We send the labeled RGB image to VLM together with a short geometric summary of each cluster, including the centroid, extent, and elongation. This helps the VLM reason over object candidates instead of predicting coordinates freely on the whole image. VLM has three main responsibilities. First, it selects the correct tool cluster for the task. Second, it predicts the grasp region, meaning where the robot should hold the tool. Third, it predicts the functional contact point, which is the part of the tool that should interact with the target object. For example, in the shelf scenario, if the robot grabs one end of the tool, the contact point should be on the opposite end so that it can push the cup out from under the shelf. To make this more reliable, we use structured chain of thought prompting instead of directly asking VLM for coordinates. We first ask it to reason about selected tool geometry, then the grasp location, and finally the opposite functional contact point. Only after this reasoning does the model output the final pixel coordinates. This reduces the tendency of the VLM to place key points near the center of the object or at non-functional regions. This was especially important in the shelf scenario. Without chain of thought prompting, only 3 out of 10 rollouts succeeded. With structured chain of thought, the success rate increased to 6 out of 10. More specifically, failures caused by placing the contact point on the same end as the grasp decreased from 5 cases to 2 cases. So the improvements mainly come from better functional contact point localization, not from changing the robot controller. Once the VLM outputs pixel coordinates, we convert it into a 3D point using the depth image and the camera intrinsics. The camera intrinsics parameters and focal lengths are given. Instead of using the depth value of single pixel, we average valid depth values in a small local region around that given pixel. This gives more stable depth estimates, especially near object boundaries. Then we back project the pixel into 3D using this equation. Here, z hat is average local depth. This gives us the point in the camera frame. We then transform it into the world frame using the camera intrinsics. If the key point lies on the selected tool, we snap it to the nearest point on the tool's point cloud. This makes the final 3D key points more physically consistent. For grasping, we use the VLM predicted grasp point to define a local crop on the selected tool point cloud. Then we run antipodal grasp search only inside this VLM guided region. This gives the final gripper pose G, including the grasp center and approach direction. The VLM also generates scenario-specific waypoints. In the wall retrieval task, it predicts one point behind the box for hooking, another point as a pull endpoint. In the screwdriver task, it predicts the screw center, and we apply an offset above it to create a safe descent pose. In the shelf task, it predicts two shelf edge anchors, A and B, which define the sweep direction. These waypoints pixels are also projected to 3D using the same camera intrinsic and depth-based back projection pipeline. So in summary, the VLM does not directly control the robot. It proposes semantically meaningful tool use key points and waypoints. Then the geometric module converts these image level predictions into precise 3D points that can be used by Grasp Planner and Como Trajectory Optimizer.
Why we use Como in this project? First of all, Como translates the VLM's high-level semantic waypoints and spatial relationships into mathematically safe executable robot trajectories. Another reason is precision tool control. Moving a tool isn't just about reaching a coordinate, it requires strict orientation. We use Como's vector objectives to lock the tools into specific alignments. Another one is dynamic waypoint navigation. The project requires interacting with objects in varied dynamic locations. We utilized Como's position diff feature to generate smooth, continuous mathematical paths between calculated 3D frames. The last one is built-in safety in constrained spaces. Because the robot operates near walls and inside narrow shelves, we integrate Como's accumulated collisions and joint limits constraints. So this ensures the arm dynamically avoids obstacles and mechanical limits without needing hard-coded avoidance maneuvers. Como wall scenario execution flow. In step 1, we do region cropping and antipodal grasp. The point cloud is cropped to a specific graspable region defined by the VLM. Within this cropped area, the optimal antipodal grasp is mathematically computed. Then, Como navigates the arm to this precise target, closes its gripper for a stable hold, and safely lifts the rake. In step 2, we do pre-pull positioning. Como completes a collision-free trajectory to maneuver the tool's functional end to a pre-pull waypoint. Then it positions directly behind the target box. In step 3, we do the pull action. The robot executes the drag motion as Como guides the functional head precisely from the pre-pull waypoint to the designated post-pull waypoint. In step 4, we do tool disposal. Once the pull is complete, Como lifts the rake over the wall and navigates the arm to an empty designated area to drop the tool. In the last step, we do target retrieval. Finally, with the target successfully pulled out from behind the wall and into reachable range, Como generates a new trajectory for the robot to grasp and secure the box. Uh, Como shelf scenario execution flow. In step 1, we do vector alignment and antipodal grasp. The VLM identifies the grasp point and functional tip to form a tool vector, as well as the shelf opening vector. Como executes the grasp and precisely aligns the tool 90 degrees perpendicular to the shelf entrance. In step 2, the safe approach. Maintaining this strict orientation to prevent collisions, Como plans a safe path to navigate the tool to an entry waypoint near the edge of the shelf. In step 3, we have downward insertion. Como smoothly lowers the tool directly downward to the operational height required to reach under the shelf. In step 4, the sweeping action. The robot performs a lateral sweeping trajectory completed by Como to drag the target object out into the open workspace, strictly holding the 90-degree alignment. In the last step, we have target retrieval. Once the target is cleared from the shelf, a final query locates its new coordinates and Como generates a trajectory for the robot to directly grasp the object. Como screwdriver scenario execution flow. In step 1, we have antipodal grasp execution. We use the VLM's defined region and comma computes and executes optimal physical garage to secure the tool. In step 2, we have vertical alignment and approach. The VLM provides an approach waypoint. Comma uses this to geometrically lock the screwdriver into a perfectly vertical orientation and navigates the functional tip directly to the target. In the last step, we have the screwing action. With the tip in position, comma executes a highly constrained rotational trajectory and performs the screwing motion without losing alignment or slipping. Moving on to our ablation study, we tested how prompt complexity impacts the VLM's spatial reasoning. We compared four prompt levels: P0 minimal, P1 structured, P2 scenario aware, P3 anti-failure. We evaluated these across our three scenarios, focusing on metrics like grasp region hit rate and grasp center variance. The results revealed clear differences across the prompt levels. In wall scenario, P0 and P1 completely failed with a 0% hit rate. However, adding coordinate hints in P2 and P3 boosts the hit rate to 80% and slashed variance from 290 millimeters to just 21 millimeters. In screwdriver scenario, P3 was the standout, achieving a perfect hit rate and 0 mm variance in the first two scenes. In shelf scenario, surprisingly, P1 was our worst performer, failing 33% of the time due to calculation errors. P2 and P3, on the other hand, achieved flawless sub-pixel accuracy. P2 is our recommended prompt here. To summarize our core findings, first, basic tool selection is trivial for the model if cluster labels are provided. Second, P1 is consistently unreliable and never recommended. Finally, P2 and P3 are highly complementary. The main takeaways is that richer prompts and cluster ensured grounding drastically reduce spatial variance and improve accuracy.
Now let's take a look at the failure cases. While our system is mostly reliable, the VLM still makes some very specific mistakes depending on the scenario. First, in the wall scenario, you can see that VLM simply selects the wrong tool. Instead of picking the right tool to pull the box, it gets confused and chooses another object on the table. In screwdriver scenario, the problem is about precision. Here, the VLM incorrectly guesses the position of the screw head. Because it gives the wrong coordinates, the robot completely misses the target. Finally, in the shelf scenario, we see another tool selection issue. Even though the task clearly needs the sweeping tool, the VLM makes a bad choice and picks the wrong item again.